Hello, everyone. My name is Ye. Today, I'd like to talk about the proving cost of ZK-EVM. So it's actually has two goals. One is that there are two goals. One is that to get you a better sense of what's the approval cost. So because you can figure out because generating proof for ZK-EVM really suffers. So you need to figure out what's the dominant computation module improver, and theoretically how many FFTs and how many multiscalar multiplications you need for generating this proof. And then you can figure out how fast and how parallel your prover can really be. And secondly, they're talking about because when you are writing custom gates and lookup arguments, what's happening in the backend. Then you will know how to optimize this circuit layout. So whether you use more custom gates or more lookups, you use a higher degree custom gates or lower degree custom gates, but with more allocated internal cells. And also you use a wider or shorter circuit, but a thinner or taller circuit. And lastly, I just want to brainstorm some discussion around around this ZK-EVM, community effort ZK-EVM, some problems we met and some possible solutions. So first, just assume that everyone is expert at ZK and ZK-EVM. So just a quick overview, you got the solidity code, you got the bytecode, and you need to fill up those witnesses in your tables. And when you are writing opcodes, you need to write a lot of custom gates. For example, in add, you need to constrain that the selector of add is open. So each selector, each cell, you write different, whether it's 0 or 1, to constrain that it's a selector. And the last line, constrain that there is only one opened. And also, you need to do some add specific constraints, and you also do some context check and those stuff. So those are the first kind of custom gates you are adding to this ZK-EVM circuit. And second kind of constraint you are adding is lookup arguments. For example, there are some operands you are operating in this add opcode. For example, you pop 2 and you push 1. So for each operand, you need to look up in a RAM table, and there will be a separate RAM circuit to constraining that this RAM table is correct. So that's basically two ways how you are writing the circuit. One is customer relationships. Second is the lookup arguments. And so the question is that what's the cost of writing those constraints and what's happening in the backend? And that's the point of this topic. So let's look at the cost of adding a custom gate. So for example, you want to constrain that the cells within that region have some relationship. You write some VA5 times VB5 times VC5 minus VB6 equal to 0. So when it's backend, you generate those polynomial relationships. So A1 is for the first column, A2 is for the second column, A3 is for the third column, and A2 omega s means the second column, but it's in the next rotation. And it's not enough because you only want to constrain that a certain position. So what you do is that you have actual selector column, and so in your polynomial, you also need to multiply with the selector polynomial. So basically, when you are writing each custom gate, you result in one polynomial identities, and each polynomial identity is a polynomial with some rotations. So basically, DJ is how many custom gates you have in your circuit, and so for each custom gate, you will result in one polynomial. And let's look at the cost of adding a lookup. So basically, what you usually do when writing circuit is that you have a tuple, and each tuple is actually some expression. To simplify, I will just write V5, VB5, VC5, and you look up this entry in some lookup tables, whether this entry belongs to that table or not. So let's look at what kind of polynomial it's generating. So basically, a traditional plookup or the lookup argument define relationship between two columns. For example, A1 column belongs to T1 column. So let's just firstly understand this. So I will give you a concrete example. Firstly, you fill up the first column with 1, 2, 1, 2, 3, 1, 1, 2, 1, 2. And then it belongs to the table only have 1, 2, 3. So what you do when you are proving for this argument is that firstly you need to sort so basically what I'm describing is the lookup using Halo 2 is different from plookup. So in plookup, what you do is that you concat two vectors and you sort something, and then you randomize the differences and you generate some constraints, some polynomials. So what Halo 2 is doing is that instead of concatting together, so for each column, it will generate some permuted column. For example, it's just some sorting of your initial column. For example, your A1, after some sorting, you get this A1 prime. And these are the new columns you generated. And for the table, you also need to using some sorting algorithm to generate those tables, those new columns. And you need to prove that those two generated columns are actually permuted from previously like your input and output. So what you do is that you have two checks. One is that some Lagrange check for boundaries, and you start with 1. And second is some, like, you generate some running sum for zx, and it's a separate polynomial. So if you don't understand too much about the crypto side, you just need to remember that for multi-side check, you need 2 polynomials. And like after you permuting this two column, what you still need to do is that this 2 permuted polynomial has this, like, membership relationship. So what you do is that, so this is like new in Halo 2. So what they do is that firstly they check that all those 2 columns start with the same element. So they all start with 1. And then, like, for the elements in A1 prime, it's either equal to the previous value or it's equal to some new entries in this table. So those are the two constraints you add. Like the first one is like you multiply with some Lagrange polynomial, which means it's constraining your starting point. And second polynomial is that this new column, whether it's equal to the previous value or it's equal to some entries in this table value. So this is a bit more technical, but like if you don't want to understand so much, you just need to remember that if you want to prove that one column belongs to the other column, it needs 4 polynomial constraints. And so if you have DJ customer gates, so sorry, I read some table. So there is like DT, like lookup tables, and then it will result in 4 DT, like polynomial identities, those four times equations. And now let's look at like because you want to sorry more. So because as I mentioned previously, you need 2 permuted columns in the middle, right? So you need to also to commit to those 2 columns. So you actually also have two additional DJ, like additional polynomials for A prime x and T prime x, which is a permuted column for your input polynomial. So let's look at, because what we are looking at when we are writing lookup, we just look up certain entries, right? So we need to only look up VA5 belong to T1. So similarly, you can write some selector there and only open at this entry, and then you still generate some new like internal like columns, and then prove that this and this has this relationship. So the only difference is that you generate A1 prime in a different way, because you are actually multiplying S column with AI column. And so this, like, your polynomial becomes Sx times Ax. And now, like, like after all, like, if you want to prove that some cell belong to a table, you need those constraints still, like, 4 times. And even more flexible, like if you want to look up a tuple, whether it belongs to some table or not, you just use some linear combination and multiply all those stuff. And you need a selector to open at a certain point, and then you need those linear combinations and prove that whether they belong to the polynomials combined from those tables or not. So it's still like 4 times larger than custom gates. So that's the only thing like you need to care about. And for this new, because like you need to generate new permuted polynomials and new columns. So you need like your new polynomial is actually some linear combination of your A1, A2, and A3 column. So that's basically like the overhead for adding a lookup tables. And like moreover, you can write some expressions there, and you just need to like combine your columns using those expressions. So at the end of the day, what you have is that you have a lot of polynomial identities you need to prove. Like for each cascade, it will result in 1. For each lookup argument, it will result in 4. And then what you do is that you need to commit to all different polynomials and open those polynomials at a random point to prove that this relationship holds at all the columns. Like, so usually what you do is that you need to divide by some vanishing polynomial. So this vanishing polynomial defines like which row you vanish. And then like because you have so many polynomial identities, and you can linear combine them to get a hx. And this hx is actually super hard to compute. And this is actually the biggest overhead for the prover. Because I will give a concrete example. Like to compute hx, you need to linear combine all those polynomial identities, right? So it's high degree, because each custom gate have degree 4 or even higher. So to compute the hx, you need to do a lot of high degree polynomial computations. And that's also a reason why you need FFT over different field. Because if you are doing FFT like for polynomial multiplication, if you are just doing like for example like your input 2 polynomials are just n degree times n degree, so you will result in some 2n degree polynomial. But if you are just doing FFT like size n FFT, so what you do is that you result in n points. which can't interpret to get your like degree 2n polynomial. So that's the reason why you need higher degree FFT and larger size FFT, because you need to coordinate with those high degree polynomial identities. And then like after you get this, you need to random that at a random point. And to get all those evaluations for those polynomial identities, you need to open each polynomial at a random point. And then you run some multi-open argument for this part. So like it's more technical, but let's look at the workflow. So there are like so many polynomial identities from your constraint system. But so for Cosmic Gate, each will introduce 1. For lookup arguments, each will introduce actually 3, because the previously your input polynomial. So here I'm talking about new polynomials you introduce. So basically, your input polynomial comes from some linear combination of your columns. So the polynomial actually comes from some linear combination of those. You already have the column polynomials. So that's for lookup arguments. And for opening, you need to commit to hx. And this is the overall workflow. The prover need to commit to some polynomial. The verifier need to generate some randomness, and then like prover commit to those lookup tables and those polynomials, and then like you calculate some hx, and then finally you open hx. Now let's look at the proving cost. To commit to ix and ax, which is the instance column and the advice column, you need to do those 2 operations. Firstly, because to get the instance or advice polynomial, so basically what you get after filling up the witness table is that you get a table full of witness, and then like to get the polynomial, you need some FFT to interpret to get your polynomial, and so basically you need that your like how many mi is the number of your instance column, and ma is the number of your device column. So you need that number of FFT, and then you also need the similar number of multi-exponentiation to doing the KZG commitment. And also like for doing like lookup, you also need that number of multi-exponentiation to commit to those intermediate like polynomials. And then like when you're open, you need to do polynomial evaluations on your coord point. So that's a third dominant part, like polynomial evaluations, evaluating at some random queries. And then when you are doing the computing this hx, you need to compute like some extended FFT, which is the larger size, which is basically your row number times your largest degree of custom gates. And then you need that number of FFTs and multi-exponentiations. So basically, you need those two components, those components as you're proving. So there is FFT, and there is FFT, and FFT is overall large domain, and you also need polynomial evaluations. So here is the overall large like cost. I will, because I'm like lack of time, I just go over quickly. So basically, if you add 1 custom gate, it will just add 1 term in your hx. It doesn't introduce actual commitment, because only if you introduce new columns, you need to commit to that. But for lookup arguments, you introduce actual commitment because you need those intermediate polynomials, and they vary in different arguments. So like some potential improvement to our circuit layout is that first you can reuse the lookup across the whole circuit, because lookup really introduces a large overhead. Like because you can open like use 1 selector column, and also those are some potential like improvement. Like you can also some expensive copy circuit to outside, because you don't want to do all the constraints in the same circuit. And also like you can change the whole layout to some wider one. Like for example, even the widest one is just say Stark AIR, because you do some row transitions. And also like you can lower the degree to some extent so that it can lower your maximum degree of your custom gates, so that you can do in a smaller size FFT. And so they say like maybe you can outsource like each row to some other circuits. And so like final just one quick mention, like in our ZK-EVM circuit, another heavily used operation is lookups. So basically, in EVM circuit, you need to look up that some column belong to some other tables, right? Some other table are also constrained by some other circuit. For example, this one. So to look up such, to build such a relationship, there are several solutions. One is that you can pad this table to exactly the same length of your input circuit. So and then you do some lookup, like whether this entry belongs to that one, and also you do some permutation, because there might be some like different order. The order in your initial column might be different from this one. And another way is that you just put everything in the same circuit, and you just directly reuse the same column. And third way is that you do some cross-circuit lookup, like you do some p-lookup stuff, because ultra-Planck or Hilo 2 implementation naturally requires you to pad the two columns into the same one to do that argument. But plookup, the initial one doesn't require you the input and output to be the same. So maybe you can do some cross-circuit lookup and add some feature to Halo 2. Because one advantage it can bring is that you can run some lower degree custom gates over those tables because they have a smaller number of rows. It's not only the lookup relationship, but also like other constraints over this circuit can be at a smaller degree. Yeah, so that's basically some optimizations and some proving cost analysis. And thanks for everyone.